Greetings everybody, welcome to the latest edition of the Conceptual Astrophysics video series. This is a series of videos in which we show how to set up and solve introductory astronomy problems. I'm your host, Dr. Christopher Cirola. Today we're taking a look at graphs. Now, why would we make a graph? What's the purpose of a graph? Well, first of all, graphs are visuals. So let's suppose you have a set of numbers and you're wondering if that set is going to tell you anything interesting about what you're looking at. Specifically, you've got two sets of numbers for the same objects, for example, and you're wondering if these two different qualities or quantities are related to each other in some fashion. Graphs can show us this. Now, I'm not going to go ahead and do every single kind of graph. That's its own course, perhaps. But let's get a start on some basic, fundamental, good hygiene, if you will, for making graphs. So, let's suppose we have the following situation. We've got a table showing a group of nearby stars. I've got the star names listed here, or their designations, and we are going to compare, or want to compare, the mass of a star to its radius. So how much a star weighs, if you will, compared to how big it is. Are those things connected to each other? Now, it might be possible, probably is possible, to look at the numbers straight up and tell if there is some sort of correlation. You get at least a little bit of a feel for that. But let's see if we can do a little bit better. And a graph is a great way to visually interpret this. So, how do I set up a graph? Now, I did this on purpose. I'm not using graph paper because I want to show up how to actually make a graph, even if you don't have graph paper, even if you don't have, say, a computer program that's going to graph this for you. Can we make a graph straight up? So, let me bring back the numbers here. First off, let's look at what we're talking about for numbers. Specifically the range of numbers, the lowest to the highest possible numbers. Now, if I look at the mass, it goes down pretty close to 0. There's the smallest number. So let's just start at 0. That's pretty easy. And if we look carefully, 1 looks pretty big, but then we go along and, 1.8 is the largest. So we need to have space to at least include everything from 0 to 1.8 solar masses. All right. Oh, quick aside. This symbol here, capital M for mass, and a circle with a dot inside, stands for the sun. And so radius, solar radii, also same sort of logic. Okay, so for the mass, we want to have that. And I'm going to put the mass on the horizontal axis. And so let's get out a standard ruler. And let's go ahead, for our purposes here, let's have a centimeter stand for each, say, 1/10 of a mass, solar mass. And I'll start here at the red line and go all the way to the end. So we'll start here, we'll make this our corner, we'll go all the way across the page, and every little notch will be 1/10 of a solar mass. I'll make a bigger notch to mark off the half masses. So half a solar mass, 1 solar mass, little notches for the individuals, and then again a little notch there, or larger notch, excuse me, to stand for that. So I've got that. Now, next thing I want to do is label the axis. It doesn't do us any good to have a nice coordinate or axis drawn unless we have labels to tell us what everything stands for. So some good approaches to do this. First off, this was mass, so we're going to write the word mass like this. And then in parentheses, I want to express what the units are. What are we expressing this in? Now, not every possible quantity has units. And so if you don't have units, of course, you don't write them. But most of them do. And I want to be able to tell what I'm talking about. So this is mass of a star in solar masses. Now, I could do a plot, say, in terms of kilograms or some other unit of mass. But this one is what we've got, and it turns out it's also appropriate. Next thing is to note. Now I'm going to start at 0 for both axes, so I'll just put a 0 there. Let's point 0.5, 1.0, 1.5, so on and so forth like that, to scale out the numbers. So again, this is a visual. This is something to always keep in mind when you're making a graph. Everything is visual. Therefore, we need to make sure everybody can see what's happening very explicitly. All right. So next idea here. Let's take a look at this. Radius also starts down pretty small and goes up to, I think, 1.6 is the maximum. So very similar. Now, this turns out to be more of a coincidence than anything else, just for this. But let's do the same thing. Now, again, let me count off little notches to stand for the solar radii in a similar fashion. And let's see, so that goes up to, there's 16, 17, 18. So I'll go up pretty much the entire scale all the way up like this. Okay. Again, little notches to represent every individual tenth of a solar radius, and big notches to stand for every half of a solar radius, like that. Okay, so let me make sure I make a count of that correctly. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Good. 1, 2, 3, 4. Up. I did that a little bit. Sorry, mistake there. 3, 4, and there we go, like that. Okay, and let me make sure to extend this all the way up. Since I've drawn it, I might as well do that all the way. Okay, I'm doing this by hand. It's a little crusty looking, but it gives us the right idea. If you were doing this for real, if you're going to turn this in, you probably want to make sure you do this a little bit better. All right, so to fit this over here in the scale, I'll just write my word turned around. So radius in terms of solar radii, like that. And the numbers I can keep as they are. So 0.5, again, 1.0, 1, 2, 3, 4, 5. This is 1.5. There's, yeah, make sure I do this right. 1, 2, 3. For some reason, I can't count today. Let's try that. There we go. 2.0. So always double check your instructors. Make sure they're doing what they're supposed to do. Okay, so we've got that. Now, last thing to do is to actually plot the data. So how do we plot data on graphs? How do we do that? Well, we're doing what's called a rectangular graph. So we just simply go over to the right and go up a set number. So this one's easy. The first one in the list is the sun. By definition, of course, the sun has one solar mass and one solar radius. So I go over 1 to this number here and go up 1 like that. Now, because the lines on my paper don't correspond to my notches, let's grab up my ruler if I want to do this a little bit more carefully. And I'll go up, so make a tiny little dot there. That's 10 centimeters up to stand for 1 solar radius. And just to check, that looks pretty good. I'm 10 centimeters over again. Now, put a nice big round visible dot at that position. Okay. Sometimes students ask, do I need to label each dot? And unless you're told to, the answer is no, don't label the dots. There's usually no need for that. We've already got the table if we need to see what an individual dot's identity is, if you will. And it tends to just junk up the picture. Remember, we're trying to see something here, right? The point is we're trying to look at something and understand what it means. And if you have extra words strewn throughout the picture, kind of defeats the purpose. All right, let's do the rest of this. I'll do this a little bit more carefully, or quickly, I should say. So Alpha Centauri B, 0.78 and 0.83. So 7.8 centimeters over. So there's 0.5, 0.6, 0.7, 0.78 is right about there. And 8.3 up. So let's go that way. So 8.3 will be 8.3 right about there. Now, just to speed this up a little bit, I'm not going to take as much care in doing everything. Let me eyeball everything a little bit just to speed it up. But if you want to do this really well, keep using the ruler. Keep using your ruler or meter stick in order to measure this really well. Okay, Barnard star is 0.28 and 0.27. That's approximately there. Wolf 359. By the way, you don't have to memorize these names of stars. I don't. If I want to know what a name of a star is or a catalog designation, I just, of course, look it up. Some of them are catalogs. So just to say this real quick, if you look at something like, say, BD plus 4344A, that's from a catalog. This particular catalog is made by a telescope, an old telescope project in Germany, for example, and that's just the number they assigned for this particular object. That's all. Others are for individual people do surveys, and so Wolf 359, right? Somebody named Wolf did that. Some are named after individual people, particularly Barnard star, and there's other examples of that sort of thing. And then finally, a very common way to name a star is by its constellation. So Alpha Cen B, what is this? That's the Greek letter alpha, and that usually stands for the brightest star in that particular constellation. Cen is shorthand for the constellation's name, in this case Centauri. And this particular star actually is part of a star system, a multiple star system, which has components A, B, and C. This is just B. I didn't pick A or C to show they're different stars. So let's keep on going with my graphing. And, okay, so Epsilon Eridani, 0.75. I know this makes for the most scintillating of visuals to watch me plotting points, so I will speed it up as best I can. But I want to show how it sort of develops. So there is a method to this madness here. And again, I'm really speeding it up just to get this kind of presented to everybody so everybody can see what everything looks like, right? Let me get my sheet out of the way for you so you can see what I'm up to. Okay, I'm getting close to finishing here. Now, again, remember the reason for all this is to, when we do plots like this, is to see something, right? So that's the idea. If we don't see it, it's not any good. We have to see it. Okay, so let's suppose we have this as our graph. Now, first things first, there's quite obvious, hopefully, that there is a trend. There's a definite trend that as the more massive a star gets, the larger it gets. Okay, just to say this for those officially interested, this is restricted to a particular group or categorization of stars called main sequence dwarfs. Yes, as strange as it sounds, there are dwarf stars. Something like the sun, which is roughly 1 million miles across, is a dwarf in this context. It's weird, but true. But we can do a little bit better than that to get maybe a visual to see this. And that's to sketch a line through the points. Okay. So something else, this doesn't happen too often, but once in a while it does. There's a tendency to want to connect the dots, right? There's kind of a tendency. And again, unless there's a very specific reason to do that, don't do that. Do not connect the dots. Instead, we're going to start at 0. By the way, a star with no mass has no radius, so 0 is a legit place to start. And what I want to do is line up my straight edge or ruler in such a way that it cuts through the middle of the dots as best I can. Now, there are mathematical tricks to do this a little more carefully. Okay, so we could, if need be, do some fancy calculations to get the actual slope of the line we're sketching. But for our purposes here, I'm going to cut it short and just eyeball it. And what you'll see is, roughly speaking, half of the dots on the low side of the line and half the dots roughly are on the upper side of the line. It gives us a flavor of the general slope or appearance of it. So in physics and astronomy places, in real life, if you will, there's no such thing as perfection. The dots will never, in a real situation, all line up exactly on the line. That's not a thing. Even if it looks like they do, chances are when you look very carefully at the data and you get it precise enough, you'll find out there is a little bit of variation, because we live in reality, not in some ideal environment. But we do want to have that doesn't mean we can't say anything about it. We do want to have some general trend. This makes sense if you think about it. The more a star weighs, the bigger it is. Okay. More specifically, it's almost a 1-to-1 setup, right? As a star gets, say, 1 mass's worth of a star, 1 radius worth of a star. Half a solar mass a star gives you close to half a solar radius. 1.5 masses gives you about 1.5. In other words, it's almost exactly a 1-to-1 relationship. Now, that turns out to not be perfect. If we were to add more stars and do a much better job of this than what I've done here, perhaps put this into a spreadsheet to let the computer do the graphing for us, we get a better sense of it. And we'd find out that maybe it isn't exactly 1-to-1. Maybe the ratio is a little bit off of that. Fair enough. But this still gives us the general trend, and it makes sense compared to what we're doing. Last thing we want to do is give a label or a title for the entire graph. That's separate. So you don't just simply say, graph is radius versus mass. Well, we already have that, right? You have radius there and mass there, so we have that. This is, for example, okay, we could say this is a sample of nearby, which they are, stars. and that would be our title. Okay, and you put that in some place like that so everybody can see what you're talking about. Okay, so to review, if you're graphing, there's some basic rules of hygiene, if you will, for graphs. One is you'll set up coordinate axes. First off, you scale it so that they include all the points. You measure, or you take a look at the original data set, you find out the range of the points, and you graph it so that you include all the data points. While we're doing this, to say it very carefully, notice that I've counted out everything evenly, like this, for the numbers, not for the points. The points are individual data points. They aren't evenly spaced out, are they? But you will see that if I space out the numbers, then I have a fair assessment. So there's another thing that happens sometimes. Students will simply put the points themselves at evenly spaced. That doesn't make any sense. Your values here for the coordinate are evenly spaced, but the dots don't have to be. They don't have to be evenly spaced this way or that way, either way, okay? We do want to label each axis, tell you what it is and how we're expressing those measurements, what those numbers stand for, how much they count. And then when you've got your points, if it makes sense, and it doesn't always, if it makes sense, sketch a smooth line through the points. There may be cases where instead of a line, you have some kind of curve. Fair enough, you can still sketch a curve. You can still kind of smoothly draw a line or a curve that goes through the middle of the point, so to speak, to get a feel for what's happening. That's still fair. And you'll see in the classes like this as you go along that that's commonly done. But the point of a graph, before anything else, is that you see it. So last comment, notice that I used the entire sheet. Okay, this is something else. For some reason, sometimes people want to save paper, or they just want to, they think it's okay to put it into a small space. I've seen graphs about as small as, say, this, and then they're drawing something that looks like this, and I can't tell for the life of me what's happening when your graph is that tiny. We want graphs that are huge. We want to be able to see everything that's happening. So, unless again you're told differently, you should always, when you're plotting something, use an entire sheet. Use as much space as you can get away with, because that's the reason for doing the graph, is it's a visual. All right. This has been Conceptual Astrophysics with Dr. Sorolla, showing you how to set up and solve interesting, or introductory, hopefully they're interesting, introductory astronomy problems. Thanks everybody for your attention, and clear skies.